This conference will now be recorded.
Okay, hi everybody. Welcome. We had August off, partly because I was blasted with 4 conferences that I decided to attend, which actually turned out to be quite good in terms of networking across different people, different businesses, and letting people know what we're up to, and actually seeing if we can get a little bit more traction. So certainly I've certainly managed to raise the profile of what we're up to here. So, and got some interesting discussions that are steadily progressing. So I wanted to spend today giving you a bit of an update on that. Additionally, put a lot more effort into the enclosure of the module. We discussed about the cooling of the drives, etc., making the module slightly wider. So to help me out with that, I did actually employ my son, Ben, who's also on the line. So I get Ben to drive the model and show us what we've done. But you'll see some sort of fairly significant changes in the way we've done the cooling. So that's that. I'll give you an update on that. And then we'll just talk briefly through some high points of the different conferences and what we're up to, or what I'm trying to move forward with a number of organizations in terms of coming out of that. So that's what we'll do. But we have a few new attendees, so maybe a few quick introductions on that. Alan, you guys did give a presentation, or one of your colleagues did, I believe. Were you? I don't think you were on for that one, were you?
Yeah, no, I did give it, not on this subgroup, but in Prague, I did do a presentation.
Ah, right, okay. Well, maybe give yourself. I'm losing track of. So maybe give yourself a quick introduction there. And
yeah, so I'm in charge of business development and sales for a small company, and what we do is a robotic fiber cross connect. So we actually have a robot that's moving the fiber connectivity, and for high performance compute clusters, specifically for the AI ML, there seems to be a lot of benefits to having that sort of capability to be able to connect all your compute equipment to memory or to the network in a designated way. So that's why I'm interested in this group, and we're talking with the hyperscalers. It's a main focus of us right now to try to introduce this flexibility into the network layer.
Yeah, I guess that's sort of complementary or similar to the optical circuit switching like we've seen on the Google TPU, but a bit slower, I guess, but still the same fundamental, your circuit switching.
That's right. So they're using a MEMS, which are little micro electrical mechanical mirror system. They can switch in maybe 1 to 2 seconds the entire connectivity, but they have a small number of ports and a high loss through the switch. We're just really a connector, but a robot has to switch it. So we're talking over a minute per connection, and they're done in series. So that's really the difference, but it is in essence performing a similar function, just slower.
Okay, great. Well, welcome aboard, Alan. Next, Ben, do you want to give a brief introduction of yourself, Ben?
Hi, yes. I'm Ben. I'm Alan's son. I've just started helping out with the 3D modeling aspect. I'm relatively new to the whole computing part of it, but gotten some 3D modeling understanding and just sort of transporting it over and trying to make it as my dad sees it. But yeah, nice to meet everyone.
Yeah, no, thanks, Ben. You've been a great help this month with me running around. So yeah, we're making some nice traction. Next, Chris, would you like to give a brief introduction of yourself?
System design engineer for engineered fluids. We do immersion cooling of all sorts of devices. So just here for basic knowledge.
Okay, so immersion and cooling, did you say?
Yes, single phase.
Okay, yeah, okay, thank you. And is that everybody? I believe that's everybody new. Yep. Okay, welcome everyone. So on that, I'll stop sharing. Do you want to share, Ben? So let me just stop sharing mine. If you want to share the 3D model, and then I can talk some of the highlights, and maybe you can show some of the detail.
Yeah, sounds good. One moment. I had to change my system preferences, so I got to restart. I'll join back real quick.
Okay. So you're in twice. We've got another new person, JQ Lau from Cloudflare. Is this your first time here? I think so, isn't it?
Yeah, this is my first time here.
Maybe a brief introduction, if you don't mind. That'd be great.
Yeah, this is JQ, system engineer from Cloudflare, working primarily on hardware designs.
Okay, thank you.
Should be up and running.
Ben, great. Okay, right. So let me just, so everybody can see this, I hope. So you can see the model pretty much looks the same. A couple of highlights on what we've done differently. We decided to increase the spacing between the drives, so we had a little bit more of a wall for the cooling, for the conduction cooled attachment of the drives to the water flow. So the module is now 118 millimeters wide, whereas it was 102. And the other key highlight, just rotating around, Ben, if you don't mind, to the back side or to the component side, you can see that we've gone from 2 water inlets and 2 water outlets to just the 1 inlet and 1 outlet. We've gone to the larger diameter Stolberly connectors. So we've actually got more area than the 2. So just took the decision to do that. And now what we've done is we've repositioned the power connectors to bring in the 48 volts. So all of this is still blind mate, and that's pretty much it. And we've completely designed the water flow for the entire module. And we are assuming that this particular design has been geared up towards the work that we were discussing with the research group from the University of Illinois, where they've done conformal coated copper on top of the module. So we're going to investigate that with them. So this design is so that we can actually build a little research demo with them. And Progress Analog, I don't think Roger's on today, but Progress Analog, we're going to build the load slammer. So we're going to build a thermal test module based on the Xilinx VP1902. So load slammer would be doing that. We're also trying to involve UCLA and borrow one of their load slammer pieces of silicon. They can actually slam 1.5 amps per millimeter squared. So we can do the load slammer Progress Analog's traditional way with discrete power CMOS devices, but we're also looking at maybe trying to leverage some IP from and devices from UCLA if possible. So so that's the basics. The lid that we've got here that's designed for the conformal coating could be modified for the more traditional, thermal grease attached copper water cooled lids as well. So, but we'd have to redesign the lid. So we've based it on the assumption of a conformal coated board at the moment. So maybe Ben, would you like to just talk us through the water flow? sort of coming in, going down the drives and up through? Just sort of walk us through the flow.
Yeah, for sure, I can do that. So we start coming into this top chamber here on this left Stolby, and I'll just pop open the top layers of these. You can get and sort of see how it comes in. And as it travels around, we've got these sort of raised areas. I'll remove everything. Here. Here we go. So you see how the water sort of comes down in between each drive, flowing between these sort of 3 different pillars. And with all 3 pillars on, we'll see that it comes down the sides of these walls, cooling the sides of the drives as it comes up, and then back up this area here, down the sides, and then back up again. I'll just pop these open so you can see inside. Here, so as you see, the water comes down through the Stolby, down here, and through the sides. After it makes its way through here, comes down this sort of center hole, and then slides between, around the PCB and into our lower chamber, where now I'll pop this bottom lid open. And we can see it sort of comes to a full open sheet. Maybe easier if I show this. Sorry. I just remove everything and watch this plate from the other side. You can see the water comes in through this bottom chamber, through the pipe from the other side, and over all of the coating, compound coating that my dad was talking about, and then comes back up through the same hole in the side here to the other side and back to where the previous Stolbys were on the top side piece. Coming up through here and through this exit Stolby. And yeah.
Great, thanks, Ben.
Hi, Ben. This is Munir. Is the water circulating? Is it enclosed container or something? How we are avoiding water to spill out?
Yeah, so go on. Well, on this one, Ben. So this one's one solid block. So the manufacturability of this is going to be a big question. So we've got the fundamental design, and we're just going to be reviewing that with one of my mechanical friends on the manufacturability. But I will talk about a company, a little startup called Fabricate that does 3D printing of heat sinks. I don't know if this is viable to be 3D printed. I know people have been concerned that 3D printing isn't a good way here. But basically, there is a manufacturability question. We've tried to think about it, but this would be an enclosed unit on this side. And then Ben, just flip it over and show the connections then. So these Stolby connectors are blind mate, non-drip blind mate connectors, but the flow between the 2 modules. So if you get rid of the top at the moment, Ben.
This piece?
Yeah, the entire top.
The entire top.
Wrong way around.
Oh, okay.
Yeah, so what you can see, the water comes up to the module. So there's a rubber seal there as it mates and gets clamped to the top lid, and similarly a rubber seal on the other side. And then the top lid itself, if you do the main the sort of stiffening bar around the board first, Ben, before your rubber gasket.
Yes.
So no problem. There we go. So I envisage that this will actually be attached and somehow sealed to the board. So either somehow epoxied or glued to the board, this stiffening frame, so that it's actually watertight. And then there's a rubber seal that goes on top of this, right, Ben?
Yes, yeah.
Yeah, you should show that.
Gaskets, yeah.
And then a rubber gasket, and then there's a lid, and then all that gets clamped. And actually, you haven't shown the big corner clamp screws yet, so show the big corner clamp.
Yeah, I can turn those on.
It bolts these two pieces together effectively. So this bolts the two pieces together, and also this has you can see they're long. There we go. They're long, so these are also the primary guideposts to the wall, and we're going to start working on the wall design now. So these will be the guideposts into the wall, and there will be a hole all the way through these pillars so that we can actually screw it to the wall. It'll be a blind mate slide in, so it will sort of sit on the wall very nicely and simply, but the screws will just be there to hold the module in place on the wall after it's been mated. Does that answer your question, Minner?
Yeah, I think there are a couple of things that you may want to consider. That obviously 3D printing, we want thermally efficient material, right? So plastic may not work here. So you want some kind of material, aluminum, copper. And the second thing that I have is in the design, because most of the heat, you're going to efficiently cool the connectors and all those things, right? But in the top side of the CPU and other things, it still needs to be addressed because that's what they're going to heat is going to generate the most, right? You want some kind of channels there that can, which essentially today we do.
Yeah. So yeah, absolutely. In terms of this conformal coating approach is researched work that's been done in the University of Chicago, Illinois. Obviously, you can put a normal. We could redesign this lid to be a normal type water chamber, which is firmly grease mounted onto the main device and gap padded onto the power supplies, etc., and the other hot devices. But we were just going to experiment because the University of Chicago says he's got some research money. So really, I wanted to get to making something with his research dollars to experiment with this idea. He did explain that with conformal coating, they can coat copper features onto the you can build up even more, so you've got more cooling area. Again, that's not my area of expertise. They claim 7 times more efficient transfer compared to a thermal greasing copper brick. It is research, so that's one little area that we're going to experiment with.
Got it. Thanks, Alan, for the explanation.
But yeah, on the bottom side, definitely we need to work on the manufacturability of that. And like I said, Ben has put this together, me and Ben have put this together. So we've got what we've envisioned in this model now. Now it's a case of how manufacturable is it. We think we thought about it, but that is that definitely is a question that isn't necessarily answered yet.
But do you have any access for I/O? I mean, usually this block would be connecting to something else, right?
Yeah. So who was asking that question?
This is Mark from Intel.
Hey, Mark. Yeah. So this side we're looking at this module mounts onto the wall. We call it a wall of compute, and then lots of modules mount onto the wall. So you've got a blind mate water and blind mate 48-volt power. So that's the I/O from a power and water perspective. Ben, if you flip over now. So on this side, we've got the connectors. Can you turn the other connectors on, the topology connectors, Ben? Yeah, if you turn everything back on except for the modules at the moment. So in this particular setup, we've got these topology connectors. You've got 4 on each side, so you've got 8 topology connectors. The ones you're looking at right now, I believe they're the ones that they're MCIOs. They're PCI Gen 5 by 8. And we are also trying to cater with these water-cooled walls. We're trying to cater for actively cooled cables so that we can cool an electrical repeater inside the cable or silicon photonics inside the cable as well. You know, if we're down at relatively low wattage levels in the order of 5 watts or thereabouts. So there are your topology connections, and then if you stare down into the middle of it, then there's media connections. So we could see these are E3.S or the EDSFF standard modules. So you can actually plug single width modules into here, and so you can have up to 16 like CXL.mem devices. But the beauty of this as well is companies like TE do make cables in this format as well. So you can actually cable out of this module. So if you wanted to have a Grace Hopper type bandwidth between two adjacent modules, you could use these media I/O as well. So you have the flexibility of media, closely coupled media, or cabled I/O to other devices. Finally, we're showing on this again PCI connectors, but we could take something like Samtec's Accelerate connector and bring Ethernet out here. So you could bring 800 gig Ethernet out on these little connectors as well. So or any custom topology, come to that. So that's the I/O portion. Does that answer the question, Mark?
Yeah, thanks. I wasn't aware of all the I/O. Yeah,
basically there's 320 transceivers, so we've got to hand here. So this
that's one of the things I've been a proponent of, conformal coding, but then everybody always throws in my face, well, what about the I/O, and how is that not going to get coded and seal off all the gold fingers on the connectors and everything? So.
Oh, well, I'd love to be able to work with you, and actually we've got Intel's attention with Air Labs, your experiments with Air Labs. So maybe we can all talk on that side of things. That's another complication, I'm sure, with the optical I/O. But yeah, I'd love to work with you on that. I'm not sure how well you're plugged in with what's going on that side, but we'll cover that in a little bit later.
Thank you.
Any other thing that we want to talk about, Ben? So the only other thing I would say we've done, you'll notice because we've put more spacing between the drives, we've managed to raise the walls that go against the front of the drives that pick up the thermal interface. So this is a biggie. Will this thermal interface be efficient? We've got we'd love one of the connector companies, hint, Samtec, etc., that we want to make some sort of we've got to get some sort of thermal connection between the modules and the copper here and the water that's flowing through it to pull the heat out of the modules. Ideally, a single width module has a maximum power 25 watts, but double width modules are in the region of 40 watts, I think, is a maximum for a double width module. Typically air cooled is mainly fins, but we're wondering if we can make a double width module still single width and cool 40 watts with this here. So we need the thermal modeling needs to be extended, but hopefully we've made this design a little bit more thermal interface between the two, so when you slide the module in. So this is completely unproven. This is a concept at the moment, and it needs thermal modeling. Ender and from Turkey has been working on the model. So I need to resync with him with this latest update. I think that's everything. So I'm a lot happier that we've got a base design. Now we got to work out if it's manufacturable and at what cost. So that's the next thing.
Another requirement challenge to throw in there is how many times do you want to remove and install those those connectors that are going to go in there that are going to interface with the thermal interface material, and do you have to change that thermal interface material out every time you change out a module? Like, where does that reside?
So these are like connector springs. So like beryllium or whatever it is they make connector springs out of. I'm assuming we'll be able to get away with some insertions. We were thinking that maybe there could be some level of gap pad underneath the two. But so that compression of that gap pad, if you did multiple ones, I'm sure could be a problem. I guess primarily once you set this up, So we've got Alan, the robotics guy. So one of the things with this wall of compute is that these modules could be serviceable by a robot. You'd have like a gantry robot in the aisle by the wall, and it'd be able to potentially service the cabling, potentially service the module replacement, and even potentially service replacing the entire module. Now there is an issue of how do we manage the cabling side of things, and that's in the design of the wall of how easy do we make it to eject these modules at various levels, and how frequent we do that is a good question. I mean, typically once you've configured a machine, it may stay that same static configuration forever, but equally with this domain specific, you might want to switch things around. Obviously changing media when the media goes down would be nice to do that, and that may be the most frequent thing if you get media that fails on you. So yeah, but that would be another good point to analyze. Okay, if there's nothing else on that, what time are we at? 8:30, so we're making relatively good time here. Oh, somebody's got a comment. Hey, Greg, good to welcome aboard. Greg Compton's just joined us. Just add in. So Ben, if you can stop sharing there, and I'll pick up again.
Yep, for sure.
In fact, right. Well, we've got a few other new people coming in. Boris Mika, is that how you pronounce it? No? Can you hear us? We can't hear you if you are talking. Well, welcome aboard, Boris. And JQ, Matt. Okay. All right, let me reshare my screen. Okay, so that was a model. So you can see we've made some interesting progress there, and now we need to. So Ben is also does a fair bit of 3D modeling. So we're actually going to try and print this, and so that I can show it at the OCP Global Summit. So people can get a bit better feel for what this looks like in reality. And we're going to move on now to designing the wall. So we need to redesign the wall slightly from where it was before, because we're now changing the orientation to a vertical orientation of the module, whereas it was horizontal. And that sort of plays nicely with the water flow. Okay, so like I said, I've been busy in terms of trying to collate everything that I've gone through in the last month. It has been a busy month for me, but talking to a number of people over in these different areas, and some things are beginning to come together. So I'll go through it chronologically here, and hopefully not jump around too much on everybody. But so the first thing, I went to the Flash Memory Summit. The main thing from this work group's perspective was that I headed an experts table on CXL. I think it was CXL applications and CXL for HPC. So it was a meet the experts evening. We had a few visitors there, and essentially I went through what we're doing in the OCP HPC sub-project in terms of our approach to doing this, and how this could be a good CXL enablement platform. So that was fairly good. In terms of my other meetings, really, in terms of highlights from that, I guess there was a lot on the CXL front. Michael Choi, the Samsung had a few keynotes just detailing everything they're doing with the CXL.mem SSD interfaces and their smart SSDs in their CXL.mem modules. So I don't think that's necessarily new for us here, except for it seems to be, everyone's doubling down on the CXL front. Was quite a big highlight of the show. And obviously what we have here is we have a nice tightly coupled module that can support these E3 format, at least SSDs and CXL.mem modules. So that was there. So educating a few people on what we're up to, so that was good. The next one was OCP. In OCP, our colleagues over in ODSA, BAPI runs, the chiplet work group, that I've been quite a part of for a while, and I've also presented on the idea of chiplet enablement, as most of you will know. And the idea here is when you look at these chipletized packages from these big vendors, they're getting bigger and bigger. I think the latest packages are in the order of 80 millimeters by 80 millimeters. And when you look at them on top of an OEM module or NVIDIA's SXM module, you sort of begin to realize that the substrates are getting so big, you sort of question yourself, well, what about making the module itself a substrate? Because the modules really just carry power and high-speed interconnect. And I've talked to a number of substrate manufacturers and proposed that we could have a pretty good architecture for chiplet enablement. And so this workshop, BAPI also is a consultant to the DOE, and the DOE wants to get more involved in I guess, enabling chiplets to the wider community, because they're obviously very vertical oriented in the big players today. And so so the DOE wants to understand how they can actually help out, so the labs, etc. So the workshop was all about trying to find out avenues of where they could help make this happen. And one of the areas that I've been pushing for a while is again in the enablement. Once you've got your own chiplet type platform, how can you maybe utilize it in a real system? And so I've been, because they've got a couple of little prototype projects going on at the moment. It's all very early on, right? Because they've got like I think the two companies is, one's the Blue Cheetah with their bunch of wires interface, and another one is D-Matrix with their bunch of wires interfaced. And so they want to prove interoperability between their chiplets, and they make a little prototype substrate to prove the various connections. So that's very low level. But as we get more and more chiplets, you actually want to put chiplets together into you know, some sort of functional product. And if they did it in the HPCM format, again, we could start a prototyping chiplet enablement community where you can plug in other devices with somebody's custom-built chiplet module. So basically, that conference was exploring different ways. There was a good few presentations. I thought that Subbu Iyer, he's a professor at UCLA with lots of chiplet work going on. Key couple of things about Subbu as well is that he was, I think, one of the chief architects of IBM Blue Gene machine, and he was the guy behind the Centaur DIMM serial memory buffer that IBM brought to you know, used in all their power devices, and now they've moved on to this OMI serial buffer as well. So Subbu is extremely experienced in the system level stuff, and he's an expert in the chiplet. When I showed him what we're up to and talked about using this our HPCM as a substrate, he said, well, okay, send me some information. Maybe we can start up some research effort here from a chiplet perspective. So he gave a very good presentation there. Discussions went well. We broke out into work groups, and the interesting output from the work group I was in and another work group was the DOE felt that they could help in some of the system level prototyping, the platform standardization side of things. And how do we move from a world of, you know, simulation of these chiplets to emulation to what I've termed chiplet in the loop. So let's say you're using an FPGA emulation from an initial simulation of your SoC you could actually emulate everything in a traditional FPGA emulation platform. And we could be a chiplet, an FPGA emulation platform. And the module we're designing from Xilinx with Xilinx VP1902 is specifically designed for emulation. So we could put some of our modules together to create an emulation platform, and potentially we could replace or add in HPCMs with some real chiplets that are created, and have some chiplets that are real and other pieces that are part of an emulation. So so the government was just saying, you know, enablement, a system level platform is something where the government maybe could help out with this standardization, and that's what we're trying to do in our work group. So making some interesting progress there. I obviously pushed the efforts that we've got going on in the workshop, but it looks like we've got this alignment of which lines up with what we're doing in this group. So I've by no means cracked this. They're saying yes, HPCM is the way to go, but it's beginning. The conversation is going in the right direction. And
Alan, on a related note, we are threatening to build a chiplet, so we might potentially get involved in using it. We could always be a pioneer, as we're going to pioneer the rest of the thing.
right.
But worth a thought. We're looking at an analog chiplet.
Yes. Okay. Well, that's true. Well, and that comes on to later discussions as well, actually. So, yeah. So, well, that's great news, actually, Greg. So thanks for that. As I said, on the substrate side of things, I've spoken to IBM substrate experts. They don't seem to think it's unreasonable that a substrate of the size of HPCM. I've spoken to Fraunhofer about it, and I got similar response from them. It's, you know, there are things that we need to resolve, but you can improve power integrity, you can improve signal integrity. There are several wins there. So that's good. I mean, the DOE is definitely wanting a modular, more upgradable approach to their supercomputers, rather than this turn one machine off and turn, you know, build a forklift and brand new machine in. They want it to be in the more sustainable, more, you know, upgradable. The embodied carbon footprint, trying to reduce that, which is all the efforts that we're putting in here. So that's good.
And to be honest, Alan, that doesn't just apply to the supercomputing. It applies to almost every computing platform they've got, actually.
Fair point. Fair point. Okay, so I'm encouraged that this is a slow train, but I'm encouraged that things are moving nicely in the right direction. So that was that. That was a good workshop. Then next came the ERI Summit, which is the Electronics Resurgence Initiative. It's a sort of a DARPA. It's related to DARPA, and this is where all the CHIPS Act stuff is going on as well. So the introductory presentations there were basically stating, look, CHIPS Act funding is plus other funding totals $62 billion at the moment, of which $51 billion is for onshoring manufacturing. And the way this was emphasized, I don't think I realized this as much, but they have emphasized that the onshoring is such a national security issue. It's up there with man landing on the moon, being the Russians, and with the Manhattan Project, the atomic bomb, and basically how they will throw a ton of money at this to make sure that we win. And so it was quite an interesting to understand that. There was a lot of presentations there. The whole idea of the summit is to show progress of the previous funding, as well as to show where they want to go. So what was I going to say? I think there's interesting opportunities there. I was actually encouraged, for those of you who didn't know, Paul Hertke, that's attended this meeting several times, from Xilinx, now AMD. he was encouraging me to try and be a program manager to make this happen, because once you become a program manager, you get access to Pentagon money. You get all the red tape gets cut, and you can fund what you're trying to do. The problem is DARPA has something called DARPA hard problems, and it really is next level research, which we're not next level research. The biggest challenge we've got is working across the system silos. And the fact that we've got to break down the silos and re-architect the data center from the ground up with a sustainability, energy efficiency perspective and a domain-specific computing, heterogeneous computing approach, which is what we're doing. And so while I was there, I had a chance to talk to some DARPA program managers and said, you know, hey, I was encouraged to do this, but clearly I'm not a good fit. Or what we're trying to do isn't a good fit, but hey, this is a hard system problem. It's not a majorly hard material science problem or anything like that DARPA usually invests in. It's just a systems problem, you know, in terms of in an open community, as opposed to the proprietary stuff going on in the incumbents. So from that, there were a ton of good presentations, which I'll come on to, specifically in the silicon photonics area, but there was a ton of good presentations. But I did have a discussion with the CEO of SRC, which is Syracuse Research Corporation. So for those of you that don't know SRC, they're basically like a huge contractor to the government. So a lot of the government employees are actually contractors through SRC. And the guy was talking that they very much do have a system level focus. So I've got a meeting. I'm flying to Durham, North Carolina mid this month to have a meeting with him and his colleagues to discuss what we're up to and to see how we can get the government to help these system level problems when you know it's not seen as DARPA hard type problems, if you see what I mean. So I'm hopeful that meeting will go well. And the other thing, so let me I just want to make sure I'm in order here. So the other thing that was very prevalent was the silicon photonics area and workshop. There's a separate workshop with discussions. So I, in the event at one of the breakouts, Intel and AR Labs had the demo, and they actually had their demo up and running with AR Labs as a I/O tile on the Intel FPGA being demonstrated there, and so basically I was trying to talk to them about how are they bringing, you know, that we could make an HPCM module. They had it in a PCI card format, and we could bring the optical I/O out the back of the board. And these discussions, I got a little bit of interest there, but I continued. AR Labs and Intel were at the Hot Chips conference the following week, and I got deep into discussions with the professor from Berkeley, that's the founder of AR Labs, the Intel guys, and the CTO and president of AR Labs, and that he was saying we were looking at an OAM module to get this into an open format, but in talking to Song, who heads up the OAM work group in OCP, you know, it doesn't look how well they can elegantly bring the optics into this system. And so I've showed them what we're up to and how the optics would come, the I/O would come in from the back of the board. And if for those of you that remember, when I was doing the chiplet enablement, I showed co-packaged a roadmap with our module from electrical I/O to to near packaged optics with active cables to co-packaged optics. And so I've explained that to them, and it would be nice if we could get their module into our format. There is definitely an appetite for that. And going back to the ERI summit, there was a ton of presentations. We weren't allowed to take any photographs of the presentations. It was a workshop that was anyway, I couldn't take the material out. You said you could ask them for their presentations, and if they want to give it to you, they can. I've not done that yet, but on a lot of the silicon photonics research, including UC Davis, UC Columbia, UC Santa Barbara, there was some really interesting research going on, and they were talking about they needed a platform themselves for how do they gradually bring silicon photonics enablement into an ecosystem. So I explained a little bit about what we were up to. And again, those of you that remember, we presented, we did send in to the DOE request for information. If you remember, we sent a paper in the middle of last year, August last year, and a chap called Simon Hammond, who is a program manager at DARPA, I believe, sorry, at the DOE, basically said, hey, we do read your papers, we did read it, I'd like to bring you in and have a chat, bring you into Washington and have a chat about what you're up to. So I mean, all of these were brief conversations, and I'm trying to nail down, I'm trying to get out to Washington at the same time as going to North Carolina to get the ball rolling there. But at the moment, I haven't managed to touch base with Simon since that meeting. So that was really encouraging. I think we can potentially get the silicon photonics community of there's so much promise, but there's so many challenges. We need a crawl, walk, run strategy. I think we need a crawl, walk, run strategy for the chiplet world, because there's so many hard things to crack on the business side, on the technical side. You need to take a steady approach there. And it looks like it's the same in the silicon photonics. There's so much goodness going on, but there's so many problems to solve. How can you, so look at HPCM as a prototyping platform first, with a vision of how it could turn into a supercomputer with the wall of compute. So we're beginning to resonate is the bottom line. So finally, hot chips came along, and so we've got the various updates. Google, I think, gave a fantastic keynote to kick the day off, a couple of days off. And they talked about their machine, but the optical circuit switching was really a standout for me. And they said, you know, in their module way, that they use the optical circuit switching to switch out failing nodes very effectively without losing performance. They could move an application between modules by doing the optical circuit switching, as well as using the optical circuit switching for actually rewiring, a bit like what Alan was saying when he introduced himself earlier today, for actually reconfiguring the interconnected devices, the heterogeneous devices in memory, etc., very efficiently by switching the optical circuit switches to change for different applications. Ayar Labs were there again, and they also had, Intel had what they called their Hive, which was a piece of silicon with 8 processor cores, but a protocol agnostic switching fabric designed specifically to be for the silicon photonics switching. So that was really interesting as well. So basically, Ayar Labs have got two devices with Intel silicon, and we could potentially make 2 HPCM modules with those two. And you could mix and match those 2 modules and optically wire them together if we enabled the passive optical connections in the HPCM. So that one's sort of that one's really hot and heavy in terms of my discussions with them. Whether it goes anywhere, we will see. But there's certainly a lot of interest in the fact that our cabled approach is very sympathetic to getting some optical enablements moving. Then IBM, to Greg's point, IBM presented North Pole, their neural inference machine, and they were super sensitive on it had to stay within hot chips. I guess IBM are just controlling it. In fact, when a press guy asked a question, he said, "I see you've got a press badge," and he refused to answer his question purely because he was a press guy. So they're a bit strange at the moment on that, but their chip, I believe, has some interesting characteristics. And again, it's a nice researchy one. If we could get this in an HPCM format, you could see how you could integrate IBM's North Pole into more traditional machines. Use it as an accelerator. And so I'll be engaging with my well-known friends in IBM with regards to seeing whether it makes sense, if a North Pole HPCM would make sense. And finally, Fabricate. Unfortunately, I had to leave before Fabricate presented because I had to catch my plane. But these are the 3D printing guys. So I'm interested to talk to these guys. They're a startup, so I don't know really how real this is at the moment. But basically, they're showing some very fine geometry features of how they can improve the liquid transfer in terms of thermal management. So again, so you can see these are small featured devices with these fins on, and whether you can conformally print this type of stuff, or how we do this. But these guys are based in San Diego. There's a heat sink, you can see there, with a 1 millimeter gap on the fins and water going through the middle of the fins as well. So they're again, I didn't see the presentation. Hopefully I'll be able to get the recording shortly. They're claiming it's low cost in compared to other approaches, the way they've done it. They're showing their machine. So I'm not so sure they're going to be able to print something as big as what we've got for the drive side, but I'm going to have a conversation with them about how we do this. And we might be able to make some of the water channels like this if we did 3D print it, to give much more thermal transfer across, like in the drive pipes. So that's
honestly, I would think there are better ways of doing it, not least because 3D printing on that scale is as slow as old boots. Trust me, I'm doing a load of it at the moment, and it is as slow as old boots.
Yeah, no, fair point. I mean the cost of all this. Yeah, so like I say, this is an interesting area. How we manufacture it. I think you might have joined too late, but Ben was showing the modeling and how we manufacture the dry side heatsink with all the water channels is going to be interesting. We're going to review that with my mechanical friend this week sometime, hopefully. So that's about it for the conferences. So lots going on. I'm hugely encouraged, especially with this new emergency act of the government saying we need to onshore. It's a national emergency in terms of the entire world is run by technology, and we've got to make sure we can do everything onshore here in the US. And I think that just bodes well for, and what we're trying to do is bringing this to an open ecosystem, which the government are really keen to do, rather than just the very vertically stovepiped incumbents.
I think we will get HPCM into DoD within 2 years if we can get our ducks in a row. There's a lot of demand there for all over the place, not just this.
Actually, on that note, are you able to give any more details on your little brief, just last minute? Just is there any more announcements you can make?
Well, basically, it's all happening. We're really looking forward to being able to kick this off. I think it's we're keen to get it kicked off in the next month. All the stars are aligning to make it happen. So let's go do it.
Okay, great. Just to close out, in terms of upcoming, so I've got this upcoming Syracuse Research Center meeting. Hopefully I'll be able to fold in a visit to Washington at the same time, but at the moment that's not looking as though it's going to happen. OCP Global Summit, I've prepared some basic slides for that. No time to show you them, but essentially I'm just giving a very high level overview of what we're up to, so people can understand without getting into the weeds of what we're doing. The principles, the sustainability, the domain specific architectures, etc. And I will be attending supercomputing, not doing anything specific there, but I will be attending there, talking to people. And that's everything, I think. So thank you all, and sorry it's a bit of a rush through, but very encouraging. All right, thanks guys. We'll call that a wrap.
Thank you.
Thanks a lot.